Hello, it's TK. In this video, we are going to discuss how to calculate the metric of R2. And of course, R2 is two-dimensional Euclidean space. Okay, so we're going to calculate the metric of R2. Now, let us first write the general form of the metric in differential geometry. So in differential geometry, the metric of any space has a general form that applies to any space, basically. We have a general form that applies to any space. And the only thing that will vary from space to space will be the metric tensor. But the general form of the metric for any space is the following. So let's write it down. ds squared is equal to g mu nu dx mu dx nu. This is the general form of the metric of any space in differential geometry. This is the general form. Now the mu and the nu, the values that they can take on depends on the dimension of the space. Depends on the dimension of the space. For example, in this case, we are calculating the metric of R2. So we are in two-dimensional space. We are in two-dimensional Euclidean space. So the dimensions of the space is 2, meaning that mu can take on either two values. Mu can take on 0, or it can take on 1. Same thing goes for nu. Nu can take on 0, and also nu can take on 1. So these indices, mu and nu, can take on two values. Okay, so we say mu and nu can take on either 0 or 1. Okay, mu nu can take on 0 or 1 because we are working in R2, which is two-dimensional space. So this is then the general form of the metric. And since we're working in R2, mu and nu can take on 0 and 1. Okay, now we are going to expand this. We are going to expand this general form of the metric. We're going to expand it. And we're going to expand it using Einstein summation. Now, Einstein summation works in this way. We sum over the repeated indices on a specific side. For example, on the right side of this expression, we've got g mu nu dx nu. So you can see that the mu is repeated. It's a repeated index. Okay, the mu is a repeated index because you've got mu here and you've got mu here. So the mu is repeated on one side, which is the right side of this expression. So therefore, we're going to sum over the mu. And the same thing goes for the nu. If you look at the nu is also repeated on one side. The nu is over here and it's over there, so it's repeated. So by Einstein summation, we sum over the nu as well because it's repeated on one side. Okay, so now we are going to discuss this step by step because I want you to see how we sum over repeated indices using Einstein summation. So I'm going to break it down step by step. So we're going to start with mu. We're going to sum over mu using Einstein summation. Okay, and of course we are expanding this metric. That's what we're doing. We are expanding it. So this is equal to the following now. This is equal to, so we sum over the mu. So we're starting with the mu. And mu, of course, can take on 0 or 1. So we're going to start with 0. We're going to substitute 0 in there. So this is equal to g 0. We're going to put nu. In place of mu, we're going to substitute 0. Okay? So we substitute 0 in place of mu. So we got g0 nu multiplied, of course, by dx, and we put 0, and we got dx, and we put nu. So we're substituting 0 where mu is. We're summing over mu. That's where we're starting, because mu is a repeated index on one side, okay? And we're using Einstein summation. So let's continue. Plus g. So now we're going to substitute 1. We've substituted 0. Now we're going to substitute 1. So in place of mu, we put 1. And we got nu. We've got dx. We put 1 in place of mu. Dx nu. All right? So that's what we have now. So we're expanding the metric. We're expanding it so that we can be able then to calculate it. All right? So now we have substituted all the values that mu can take on. And that's, of course, 0 and 1. Now we are left with nu. So again, nu is a repeated index on one side. We've got nu. If you look at the first term on the right side, look at the first term on the right side. We got nu here, and we got nu there. We got nu here, and we got nu here. So it's a repeated index, as we saw even before. It's a repeated index on one side. So we're going to continue then to expand this. Okay, we're going to continue to expand it by now summing over nu. We're going to sum over nu. So the first thing, this is how you sum over nu, okay? You approach it like this. This is equal to the following. So now we substitute, where nu is, we substitute the values that nu can take on. So nu can also take on 0 or 1. So we're going to substitute the values that nu can take on. But when we substitute, we have to substitute in each term. We have to substitute in each term in the sum that we already have. So the sum we already have is this sum over here, of course. So now in each of these terms, when we substitute 0, we're going to substitute 0 here, and also here and here. Okay? So we're going to substitute there, and then we're going to add that to the same sum, but then we want to substitute 1 in each term. Okay? And how that works is the following. Okay? How that works is the following. So let's just do it and see how it works. Let's do it and see how it works. All right? Okay. So now, this is equal to the following. So now we're going to go ahead and substitute into nu. We're going to substitute 0 in each term. So we're going to have 0, 0, dx 0, dx 0. So we're substituting 0 where nu is. And we're going to substitute 0 in each term. So we're going to go g, 1, 0, dx 1, dx 0. So we substitute 0 into each term. And then we sum that to the following. Now we substitute 1 into each term. Say g 0, we substitute 1, dx 0, dx 1, plus, and then now we substitute 1 in the second term. We go g 1, 1, dx 1, dx 1. Okay, so now we've expanded. Now we've basically done the whole expansion. So now there's nothing else to substitute because we've done the whole expansion. Okay, what we have to do though, we have to find out, or we have to calculate the following. We have to find out the values of the metric tensor. So G00 is basically a component of the metric tensor. G10 is a component of the metric tensor. G01 is a component of the metric tensor. And G11 is also a component of the metric tensor. And this metric tensor that we're working with here is the metric tensor of R2. So we have to know what the metric tensor of R2 is so that we can substitute these components in there. So what is the metric tensor of R2? What is the metric tensor of R2? That's what we have to find out. So now, the metric tensor of R2 is given by the following. We are going to write this metric tensor of R2 in matrix form. We're going to write it in matrix form. Okay, so we're going to say we're going to say where the metric tensor, so this is how you denote the metric tensor, okay? And then we're going to write it down. We are not going to go through the process of calculating the metric tensor. We're just going to write it down for this video. So in this video, we're not going to go through the process of calculating it, okay? We're just going to write it down. But we will go through that process of calculating the metric tensor in a different video. So in this video, we're just going to write it down. So the metric tensor of R2 is given by the following. So we got 1, 0, 0, 1. This is the metric tensor of R2. Okay, let's go back. All right. So this is the metric tensor of R2. So we're going to write 0 here, write 1 here. And that's the metric tensor of R2. So now, therefore, G00 is this entry here. It's 1. And G01 is this entry here, which is 0. G10 is this entry here, which is 0. And G11 is this entry here, which is, of course, 1. So that's basically what these entries are. So now we're going to substitute these entries into over here, into each of these components there. And then basically we're going to finish up the expansion. We're going to write the final answer. Okay, so let's go back. Let's go ahead and do that. Okay, let's go ahead and do the substitution. Okay, so we say, therefore, our metric tensor, okay, we say, therefore, just go back here. Okay, we say, therefore, our metric tensor, okay, let's go back again. Okay, so we say, therefore, our metric ds squared is therefore given by the following. So we got G00, so we substitute. So G00 is basically 1. So it's 1 multiplied by dx0, dx0. Now dx0 times dx0 is basically dx0 squared. So we can write it as just dx0 squared. And plus G10. Now G10 is 0. Okay, G10 is 0. So we can just say plus 0. So that term is just going to be 0. And plus G01, say plus G01. Now G01 is also 0. Okay, so they are the same. So G10 and G01 are the same. They are both 0. And plus G11. Now G11 is 1. So substitute 1 in there, multiplied by dx1. So this will basically be just dx1. It'll be dx1 squared. Okay, so that's what it is. So when you write it concisely, this implies that dx squared is then equal to the following. So it'll be just dx0 squared plus dx1 squared. So that is the metric of R2. But usually, when dealing with R2, what we do is that we let x0 be equal to x. We denote x0 with an x. We say we let x0 be x, and we also let x1 be y. Okay, so we let x0 be x and let xy be y. So therefore, our metric then will become the following. We can write the matrix as ds squared is equal to dx squared. Let me write this s again. It looks a bit funny. Okay, let me write the s again. So it's ds squared. This is equal to dx squared plus dy squared. So this is the metric. This is the metric of R2. And that process we just went through is how you derive the metric of R2. Okay, so this here is our final result, which is the metric of R2. Thank you for watching the video. If you like the video, please press the like button and subscribe to the channel. If you have any comments, you can drop a comment in the comment section. If you have any questions for me, you can ask me the questions in the comment section, or you can drop me an email. My email address is available on my YouTube page. Thank you for watching. Cheers.